All right, hello everyone, and welcome back. After a brief vacation on my part, we're going to jump right back into where we were. Last time, we talked about stellar lifetimes, what stars do for the millions and billions of years that they're around. And we briefly touched on how they die as well. So tonight, we're going to end this little three-part mini-series on stars by talking about the stellar graveyard. What are those remnants that are left behind when a star finally dies? Before we get to that, as always, here's tonight's quote. Now, my suspicion is that the universe is not only queerer than we suppose, but queerer than we can suppose. That's JBS Haldane from his book Possible Worlds in 1927. So you've heard it here first. The universe is pretty gay. We're going to start off with white dwarfs. We've at least mentioned white dwarfs a lot in these past few weeks. Remember that white dwarfs are essentially just the exposed cores of these stars, these massive stars that have shed their outer layers in planetary nebulae. One of those planetary nebulae is in the background image of this talk, and it's the Helix Nebula, where the bright, beautiful, shining gas is the remnants of that long gone star, and at the center of the Helix Nebula is sitting a white dwarf, the core of that dead star. Now remember, white dwarfs, as the name suggests, are incredibly tiny, but they have a star-like mass. Imagine, and we'll talk about this in a moment, imagine an Earth-sized sun. That is essentially what we're talking about with a white dwarf. But there's no longer any fusion happening in white dwarfs. All the fusion happened during the star's main sequence lifetime and as it moved off the main sequence. Once it gets to the white dwarf, all the fusion has stopped. So it is shining from just purely radiating away that heat that it had being the core of the star. The thing that is supporting it against gravity, continuing to collapse it and compress it further, is electron degeneracy pressure. As always, I encourage you to go back and watch the talk about quantum mechanics to get a deeper understanding of what degeneracy pressure is. But essentially, it's a result of the Pauli exclusion principle saying that electrons don't want to be too close to one another. You can have two electrons sitting on top of each other. They want to have their own space. And that will exert a pressure, an outward pressure against the force of gravity. So there's no fusion generating energy pushing against gravity here in a white dwarf. And indeed, there won't be any fusion in any of the things we talk about tonight. For a white dwarf in particular, we're talking about electron degeneracy pressure that's supporting it against that inward crushing force of gravity. Now, as I just mentioned, white dwarfs are the dead cores of stars. So essentially, that means their composition is the same thing as the star, essentially whatever was happening last in the core. So very, very low mass stars, less than the mass of our sun, won't ever get to a point where they can fuse helium. So as they die, they'll just have a bunch of helium sitting in their core. So a white dwarf that forms from a very low mass star will be a helium white dwarf. It'll just sit there forever. Low mass stars around our sun's mass will, towards the later stages of their life, fuse some helium into carbon in their core. So they'll just leave carbon behind, which means we'll get a carbon white dwarf. Intermediate mass stars, remember that's between 2 and 8 times the mass of our sun, will leave behind white dwarfs also made of carbon, maybe some heavier elements. But as we talked about last time, definitely not iron. You make iron, you're going to go supernova and you won't leave behind a white dwarf. So, for example, the brightest star in the night sky is Sirius. And although you can't tell it by eye, you need a very good telescope to tell it. Sirius is actually a binary system. So down here in the bottom right is an image of the Sirius system. Where the brightest star is, I think, is a main sequence A star, just living out its normal life. But right where my arrow is pointing to is Sirius B. Sirius B is a white dwarf. It's a carbon-oxygen white dwarf. So that means that its progenitor was an intermediate mass star, because in order to produce that carbon oxygen, you need to have been able to do that in the later stages of your life, and only those intermediate mass stars will be able to produce the oxygen. So that tells us something about what Sirius B was like before it was a white dwarf. Now, this image makes Sirius B look really tiny and insignificant compared to Sirius A, the brightest star. And it is pretty dang tiny. The dwarf name is true. It's pretty dim. White dwarfs do not produce a lot of light. But in terms of stars, it is incredibly, incredibly dense. A typical white dwarf has a mass of the sun compressed into a volume the size of the Earth. So Sirius B has a mass of about 1.1 solar masses, but it is a size slightly less than that of Earth. So that is just absolutely insane. And when people started discovering and realizing what white dwarfs were back in the early 1900s, they also thought it was insane. So here's this quote from famed astrophysicist Arthur Stanley Eddington. And he said in 1927, he said, we learn about the stars by receiving and interpreting the messages which their light brings to us. The message of the companion of Sirius, when it was decoded, ran, I am composed of material 3,000 times denser than anything you have ever come across. A ton of my material will be a little nugget that you could put in a matchbox. What reply can one make to such a message? The reply which most of us made in 1914 was, shut up, don't talk nonsense. So even astronomers, when we first discovered it, couldn't wrap our heads around it. And I imagine astronomers are still having a hard time really conceptualizing and understanding the fact that we've got a star the size of the Earth. That is absolutely insane. And an even stranger thing happens, where as you increase the mass of a white dwarf, its size actually decreases. You don't get bigger in size the more massive a white dwarf is. The reason for this is the more massive white dwarf is smaller is because its greater gravity can actually compress it to a much higher density, actually squeezes it a bit more, making those electrons in the white dwarf move faster, which generates a stronger degeneracy pressure to resist gravity. So more and more massive white dwarfs get smaller and smaller. You can see that here if you look at the green line, the one labeled relativistic Fermi gas. We're not going to get into what that means. But say a white dwarf of 1 solar mass has a radius of just under 1/100th the size of the sun. Meanwhile, a white dwarf of 1 1/4 solar masses has a radius of 0.5% of the solar size. So as we add more mass to a white dwarf, it will get smaller. However, there is an upper limit to how massive a white dwarf can be. Because a property of the electrons, because of the Pauli exclusion principle, as you pile more and more electrons, is not a property of the Pauli exclusion principle, excuse me, this is Heisenberg's uncertainty principle. As you put more and more electrons, force them into a tighter and tighter area, you narrow down the locations where they can be. So you lose track of their momentum. So their momentum continually grows as you narrow down where an electron can be. So their momentum, their velocity will reach the speed of light. And the only thing that can go at the speed of light are photons, is light itself. So since electrons can't move faster than the speed of light, there is an upper limit to the white dwarf masses, and that is about 1.44 times the mass of the sun. That is known as the Chandrasekhar limit, named after that guy on the right, Subhmayan Chandrasekhar. It's a hard number. You will never find a white dwarf of 1.5 times the mass of the sun. The biggest white dwarf you can find is about 1.43, actually. All right, now if it was just a white dwarf sitting by itself, then it is just going to radiate away all of its leftover energy for the rest of the universe. Theoretically, once it's done all that, it will cool to reach the ambient temperature of the universe, about 2.7 Kelvin. And become a black dwarf. We have not found any black dwarfs. We don't think the universe is old enough yet to have black dwarfs in it. But if a white dwarf is in a binary system, that is where the star can, in a sense, come alive again. So let's imagine that we've got a binary system where one star is a white dwarf and the other is a main sequence or even a giant star. Well, then something interesting can happen. If they're pretty close together, so they're not orbiting really far away, but if they're pretty close together, then that white dwarf, with its concentrated mass, its high density, can actually pull the outer layers of its companion star and cause it to form an accretion disk around the white dwarf. That in falling matter, the outer layers of that companion star will fall into orbit around the white dwarf. And because it will follow Kepler's laws, which we talked about many, many, many weeks ago, the gas that is closer to the white dwarf will move faster. You know that because planets closer to the sun move faster than the planets further out. So the gas that's closer to the white dwarf is going to move faster than the gas further out. And that'll actually exert a friction. There'll be some friction force in the accretion disk, and that friction will cause the gas that's closer into the white dwarf to lose some orbital energy and will actually fall onto the surface of the white dwarf. And it will start to sit there. This hydrogen that was once on the outer layers of the companion star is now just sitting on the surface of the white dwarf. And this is very cool. We've seen similar things in this before when we talked about how stars form. This is very similar to a protostellar disk, except the temperatures in a protostellar disk when it's forming a protostar are very low. Meanwhile, the accretion disk around a white dwarf, because it's being ionized by the high temperatures of that white dwarf, the temperatures in the accretion disk are going to be way, way hotter, which will actually lead not to the production of infrared light, like in a protostellar disk, but actually to the production of visible, ultraviolet, and X-ray light. So that same image we saw of the Sirius system, that was in visible light. On the bottom right here is an image of the Sirius system in X-ray. And now the dimmer one is actually the main sequence star, is the Sirius A. The brighter one is Sirius B. It generates a lot of X-ray light. You certainly don't want to be living on a planet orbiting Sirius B. You'd be bathed in X-rays. It would not be good for you. Now, there's something interesting. As all that hydrogen is falling on to the white dwarf, something interesting can happen. Essentially, because it is so, because all that hydrogen is piling onto the white dwarf, and the dwarf has such a large mass concentrated in such a small area, gravity will compress the hydrogen sitting on the surface of the white dwarf, which will increase the temperature and pressure. Remember the ideal gas law, Pivnert, if you're from chemistry class. Gravity will increase the temperature and pressure in the surface hydrogen until that hydrogen reaches about 10 million Kelvin. And suddenly we've got fusion rapidly starting on the surface of the white dwarf where all the hydrogen is sitting. Not inside. The white dwarf itself is not doing any fusion whatsoever. But the surface hydrogen that's fallen onto it from its companion star will start to do fusion. And this happens in a flash. It lasts for maybe a few weeks. We call this event a nova because it's less luminous. It doesn't produce as much light as a supernova, but is still as bright as 100,000 suns. We see novas all over the place. There's one in 2013, I believe, and there's definitely been one more recently in our own galaxy. Here's an image of the remnant of Nova Persei in 1901. Seen in optical light. The white dwarf is sitting at the center, and all this red stuff, that is stuff blown off, the hydrogen that's been blown off of the white dwarf there. And this process repeats over and over again as long as the companion star is still able to funnel hydrogen to the white dwarf. This will keep going. The nova burns off all the hydrogen sitting on the surface of the white dwarf, and then it'll just grab more from its companion star, falling back on the surface. And this probably, on average, repeats every 1,000 years. You'll see a nova from the same star every 1,000 years. So look back at this star in the constellation of Perseus in 2901, and you might see another nova. So in a way, a white dwarf can continue living beyond its death. It can continue to do some sort of fusion there. Now, on rare occasions, on rare occasions, a white dwarf that's sitting in a binary system can actually reach the Chandrasekhar limit of 1.44 solar masses. When that happens, oh, it's over. for the white dwarf. The white dwarf itself will explode itself apart. The way you can get to this Chandrasekhar limit is through two ways. Either you've just been accreting enough matter from a companion star, a main sequence giant star, or if you've got two white dwarfs in a binary system and they merge, that will obviously cause it to reach above that Chandrasekhar limit. When that happens, the conditions are just right enough for carbon fusion to happen instantaneously in a few seconds, all throughout the white dwarf, on the surface all the way down to the core, and that will rip it into pieces. Once this happens, there's nothing left of the white dwarf. You can go look in that same area of space where you just saw this new kind of supernova, and you will not see any star, any remnant at all. Now, what's great about this, and we'll talk about this in a few weeks when we talk more about how we measure distances in the universe. The great thing is that since all white dwarfs explode once they reach this mass, then the amount of light that they emit should theoretically be the same. Thus, if we see a white dwarf supernova in another faraway galaxy, then we know how much light it actually emitted. We can obviously measure how much light it appeared to have emitted, its apparent brightness from here on Earth, and then we get an easy distance to that galaxy. This happened in the galaxy I study, Messier 101, the Pinwheel Galaxy, back in 2011. A white dwarf supernova happened, and we were able to get a pretty accurate distance to that galaxy. Here is a little animation about how two white dwarfs spiraling in and exploding. And notice at the end, there was no star remaining. When a white dwarf goes supernova, we got nothing left of it. All right, the other stellar remnant we're going to talk about tonight is a neutron star. Now, a neutron star, just like a white dwarf is a very tiny star, a neutron star is just a big ball of neutrons. This is only created through a massive star supernova, greater than maybe 5 or 8 times the mass of our sun. Neutron stars are also very, very tiny, just about 10 kilometers, the size of maybe a large city, about 6 miles, maybe not a large city, the size of a small town in radius, but way more massive than the sun. And here, you see an artist's interpretation of what a neutron star might look like there on the left. Here, instead of electron degeneracy pressure, neutron stars are supported by neutron degeneracy pressure, which exerts a much stronger force than the electrons. Here, when a neutron star was formed, all the electrons and protons actually combined in an instant to form neutrons. And neutron degeneracy pressure is what staved off even further collapse into a black hole, which we'll talk about towards the end here. We have no idea. Neutron stars really start to mess with our ideas of matter and physics, actually. It's very interesting to see different theories. I've presented in class theories about what's going on inside of a neutron star. And one of my friends several years ago actually helped with research on what's happening inside of a neutron star. It gets very complex. It really does break down our ideas of what matter and energy and physics should be going on inside of a neutron star because of the huge densities and the weird materials. So the surface is probably very similar to a white dwarf. It's a very similar pressure. So maybe it's covered in some electrons and some positive ions. But deeper in the neutron stars where all the neutrons lie, although they could also be in some very weird states themselves. It could be a superfluid where matter flows without experiencing any friction, or maybe also superconducting, where electricity can flow without any resistance. Maybe the very center, as this model here proposes, instead of neutrons, it's instead what neutrons are made out of, quarks and gluons. We simply don't know. And literally, there's no way for us to figure out. We can't just crack open a neutron star to figure this out. So it's really testing our ideas of physics and of atomic physics in particular. Now, neutron stars, there's something special about them. Neutron stars were first thought of in the 30s, in 1933, by Walter Baade and our man Fritz Zwicky. But they weren't discovered for another 34 years until 1967, when Jocelyn Bell Burnell, she's just Jocelyn Bell back then, she discovered a source of radio waves. She was a grad student. She was working with her advisor on a huge radio telescope. And she discovered this source of radio waves. In fact, and you can turn those radio waves into sound. This is probably what it sounded like to her when she found it. Okay, there it is. They actually thought it was like, they nicknamed it LGM for Little Green Man. They weren't sure if it was aliens or not. But today, we know they are not aliens. We know that these pulsating radio sources are called pulsars. And in 1968, we detected pulsars at the hearts of the Crab Nebula and the Vela Nebula, both left behind by supernovae. So we know that these are neutron stars. They're doing something weird. In fact, here's what the Vela one sounds like, I think. Very rapid. So what are pulsars? Pulsars are actually just spinning neutron stars. They're going very, very rapidly. Spinning rapidly as a result of the law of conservation of angular momentum. So let's rehash what happens to form a neutron star. So neutron stars are only going to form from those massive stars that have done the horrible thing of producing iron in their core. So as that iron core collapses into a neutron star, first of all, those electrons and those protons are going to combine to form neutrons and exert neutron degeneracy pressure to stop the collapse of gravity. But as it's collapsing, the rotation rate will increase as it shrinks in size. You know this if you've ever spun around in an office chair. I'm not going to do that because I will get sick. But if you spin around with your arms held out and then pull them in, you'll spin a bit faster. Same thing is happening here in the neutron star. As it's shrinking, it's whatever rotation rate the star had at the beginning, it will increase as it shrinks in size. That collapse will also compress any magnetic field lines that original star had. It's going to compress them much more tightly and amplify the strength of its magnetic field. So pulsars are incredibly magnetic objects. They have magnetic fields around 1 trillion times stronger than the Earth's. This will also cause beams of radiation to emit out of the magnetic poles, although we still don't know exactly how this happens. But what essentially happens is those radio pulses, that is the radiation beam pointing at Earth and then sweeping by Earth. Like a lighthouse effect. So here you can see an animation of that happening. Notice we're only getting one bump here, even though there are two beams. The second beam isn't pointing straight at us. So that means that here's a general rule then, that all pulsars are neutron stars, but not all neutron stars are pulsars. It's only a pulsar if its beam is pointed towards us. So that's how we have seemingly normal, just sitting around neutron stars, and then active beaming radiation pulsars. Now, just like white dwarfs in binary systems, neutron stars in binary systems can sort of come back to life as they can rob material from a companion star. However, neutron stars are way more dense, way more massive than white dwarfs. They can reach higher masses. And so it has a much stronger gravitational field and is able to release way more energy than a white dwarf. So as a neutron star is stealing material from its companion, just like a white dwarf can sometimes do a nova, neutron stars can actually emit 100,000 times more energy in X-rays than the sun emits across all wavelengths combined. You really don't want to be on a planet around a neutron star. And that accreting gas will actually add angular momentum to the neutron star, which will actually increase its pulsation rate, resulting in millisecond pulsar. So I'll play you an audio clip of the millisecond pulsar, and you can probably scarcely even distinguish the individual pulses. Sounds more like a hum than individual pulses. That's how fast it's going. Now, just like accretion onto a white dwarf can cause a nova, accretion onto a neutron star can cause an X-ray burst, where instead of a sudden ignition of hydrogen on the surface, we get a sudden ignition of helium on the surface. So how this works is as hydrogen from the outer layers of its companion star falls onto the surface of the neutron star, we get a layer about a meter thick, the bottom of which is doing hydrogen fusion. Seriously. We've got a meter thick, maybe about this much, at the bottom bit is doing hydrogen fusion, building up helium on the direct surface of the neutron star. And as more hydrogen is piling on top of it, the pressures and temperatures of that small little helium layer are increasing and increasing and increasing until it reaches about 100 million Kelvin, which is the temperature necessary for helium fusion. So all that helium that's built up is going to fuse all at once and generate tons and tons of energy in the form of X-rays. It's going to release all of that energy in just a few seconds and do that every few hours to every few days, releasing about 100,000 times the power of the sun in just X-rays. Up at the top right is a plot of a neutron star undergoing an X-ray burst. And you can see where its normal level is, and then in just a second and a half, it's released so much X-rays, way, almost 3 or 4 times its normal level. These are incredibly powerful, explosive events. And although rare, neutron star binary systems, just like having 2 white dwarfs in a binary system exist, neutron stars can exist in binary systems with each other. And as they orbit each other, they will radiate away energy in the form of gravitational waves, and eventually they will merge. We have detected for the first time back in 2015, 2017, neutron stars actually merging together. And the great thing about neutron stars merging is that they produce all of the heavy elements that we're familiar with. So anything here colored in purple, is an element that is produced in merging neutron star. So that means the platinum in your plates and silverware, the gold and silver in your jewelry, the tin that we use tinfoil on, the uranium that we put in our nuclear reactors, all produced by neutron star mergers. And the great thing about neutron stars merging, as opposed to black holes merging or a black hole and a neutron star merging, is that neutron stars merging actually generate electromagnetic waves. So as soon as we detect those gravity waves, we can go point all of our optical telescopes at the direction of which we believe it came from. And we actually see the flash of light, the remnant, the decrease of light. And that's what you're seeing here. I forget which galaxy this is. Probably just has a catalog number. But that's what you're seeing. You're seeing the flash and fading light of 2 neutron stars merging. This is an amazing test of multi-messenger astronomy, using both gravity waves and electromagnetic waves to study neutron star merging. All right, and the final remnant we'll talk about tonight, everyone's favorite, are black holes. So a bit of a history on black holes. So Black holes are not as recent a thought as you might think. The idea of a black hole was actually first proposed in 1784 by the British philosopher and clergyman John Mitchell. We don't have a picture of him at all, sadly, but he proposed that there could be objects whose escape velocity was greater than the speed of light. The speed you need to leave the object, I think on Earth, it's about 11 kilometers per second. That could grow to be the speed of light. And he was the first person to propose that. And it went sort of unnoticed for many, many centuries. Only recently have we given him the credit he deserves. But where we really got the idea of black holes was when the physicists and astronomers like Albert Einstein, Carl Schwarzschild, and John Wheeler used general relativity to show that they could exist. Of course, Albert Einstein inventing general relativity. Carl Schwarzschild actually was the first person to solve the equations of general relativity and introduce the concept of a black hole. And John Wheeler is the person who named them black holes. So let's talk about the anatomy of a black hole. I've got a black hole there on the right. First of all, you see this white boundary. It's not going to actually be white in real life. But that boundary between the inside of the black hole and the outside universe is what is known as the event horizon. This is the point of no return. And it's the point of no return because space-time is so dang curved near the event horizon that nothing can escape it, not even light. The fastest thing in the universe, light, it cannot escape. It cannot climb out of that well of the event horizon of the black hole. It'll be like climbing out of an infinitely deep hole in the rubber sheet analogy of space-time. The sizes of black holes, that was what was derived by Carl Schwarzschild. He was fighting not only an autoimmune disease, but also literally with the German army on the Russian front of World War I. In the trenches, while they were fighting, he was working out general relativity. And his solution gave him the size of one of these black holes, the size of the event horizon, and we call it its Schwarzschild radius in honor of him. Sadly, he died just a few months later, not in the trenches, but due to the disease he was fighting. And so he never knew all the successes that he rightly gets. So if you want to figure out what your Schwarzschild radius is, if you compressed all of your matter to one particular size to form a black hole, I've written out this formula for you. All you got to remember is that number in front of it, 1.5 times 10 to the minus 27 meters, and then multiply it by your mass in kilograms. So this leads us to an interesting observation that the size of a black hole only depends on its mass. It doesn't depend on its composition, it doesn't depend on how fast it's spinning, only depends on its mass. And so you can see on the right in this table, I've compiled the Schwarzschild radii for different objects. If we were to compress all of these objects to, if they're Schwarzschild radius, it would form black holes. So for a human, a 70 kilogram human, if you compressed myself all the way down to a size of 10 to the minus 25 meters, very, 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 very tiny, you would make me into a black hole. If you compress the entire size of the Earth, the entire mass of the Earth, down into a ball about a centimeter in radius, it would be a black hole. If you compress the Milky Way, the entire galaxy, into a ball with a radius of about a quarter of a light year across, it would be just one big, well, actually, one relatively small black hole. So these are insane objects. Now, there are three fundamental properties of a black hole. The mass is the most important one. And that's because a collapsing stellar core will become a black hole the moment it shrinks past its own Schwarzschild radius, disappearing behind its own event horizon. So the black hole still contains that mass, but its outward appearance tells us nothing. Every black hole looks like every other black hole, despite having different masses. It hides all the information about it. You could throw in a kilogram of gold and nothing would change. No, there would be no change on the black hole to tell you that you threw in a kilogram of gold instead of a kilogram of lead. Absolutely nothing would change. Just the mass is important. And aside from its mass, the other two properties are electric charge and angular momentum. Now, electric charge it's more of just a theoretical plaything, really. Because if you have, say, a negatively charged black hole, it would rapidly attract a bunch of positively charged things in its area, becoming very quickly neutral, electrically neutral. So it's not like we're going to be finding positively charged black holes out there. It's more of a theoretical plaything. But angular momentum is very important. How fast, how much it's spinning. Because a rotating black hole can actually physically drag the space-time around it. This is called frame dragging, which will actually accelerate in-falling objects in the direction of rotation, which prevents things from just falling straight in. So my previous animation just had all my little words fall straight in. Instead, they should have done something like this, where they kind of rotate and fall into the black hole because of the frame dragging. Now, what's inside of a black hole, I hear you ask? Well, we cannot answer that question observationally, even in principle. And because there's no way for us to, we could certainly enter a black hole, but there's no way for us to send that information back outwards. Remember, not even light can escape a black hole. However, our theories can help elucidate what's happening inside of a black hole. Our current understanding of physics tells us that all of the matter inside of a black hole should be crushed to an infinitely tiny and dense point at the center, which is we call a singularity. Now, general relativity predicts that a singularity is just an infinitely curved region of space-time. Meanwhile, quantum physics predicts that space-time should fluctuate chaotically near the singularity. So our two big theories of physics disagree with each other, and that's bad. We are waiting on the really, really, really smart people, not me, way smarter people, to come up with a grand unified theory of physics that merges general relativity and quantum physics into one another. But until then, we simply have no idea what is actually happening inside of a black hole. Now, can we go inside of a black hole? Well, yes, we can. If you were to go inside of a black hole, you're going to go visit a black hole. First, we might want to test general relativity. If we're near a black hole, we might as well do that. General relativity, if you remember from our talk several weeks ago, will tell us that as the force of gravity gets stronger, time should run more slowly. And it will also predict that the light coming out of a strong gravitational field should show a redshift, which we call gravitational redshift, that is due to gravity rather than the Doppler effect. So you could test these predictions with the aid of two identical clocks whose numerals glow with light. You keep one clock aboard the ship and push the other one with a small rocket attached directly into the black hole. And that small rocket automatically fires its engines just enough so that the clock falls gradually towards the event horizon. And sure enough, the clock on the rocket ticks more slowly as it heads towards the black hole, and its light becomes increasingly redshifted. When the clock reaches a distance of about 10 kilometers from this 10 solar mass black hole, you will see it ticking only half as fast as the clock on your spaceship, and its numerals will become red instead of blue. Another thing that will happen, you can also jump into the black hole if you'd like. You would actually not feel anything as you pass through the event horizon. It's a mathematical boundary. It's not a physical one. It's not like you're crashing through a wall. You're just passing smoothly through it. So you yourself falling into the black hole would be perfectly fine. However, to an outside observer, they will never see you pass through the event horizon. From their point of view, you will take literally forever to pass through the event horizon. What they will see is your image slowly getting redshifted on the surface of the black hole until they have to look into the radio to see your image. And you'll just stay there frozen, even though you have already passed through the event horizon. Sadly, you won't really live to experience the event horizon, since as you get closer to the black hole, the force of gravity from that black hole will be stronger on your feet than on your head. So we'll pull strong on your feet, so it'll actually bisect you into two parts. And then each of those parts will bisect into two parts, exponentially growing. This process, this stretching process, has been given the creative name of spaghettification. You will literally be spaghettified as you fall into the black hole. Now, this is for a stellar mass black hole. If you want to go fall into a supermassive black hole, like at the center of a galaxy, those are big enough that you might actually survive passing through the event horizon for just a little bit. But of course, there's no way to tell us that you survived because light can't escape past the event horizon. So, kind of a moot point there. You're kind of screwed either way. Now, if you want to make a black hole, you need to have the remnant of a massive star after it's blown away its outer layers to have a mass greater than 3 to 4 solar masses. And then a black hole will form without going through the white dwarf or the neutron star phases. Here's an actually incredibly accurate movie, GIF, of what a black hole looks like with an accretion disk around it. This is due to the effects of general relativity. So because of GR, in front of us, we see the accretion disk orbiting black hole, and then it kind of bumps upward. That is the accretion disk that's behind the black hole. And this little loop down here at the bottom is the underside of the accretion disk. Because of the way GR works and light travels around a black hole, you will actually see all parts of the accretion disk as you get closer to the black hole. So the movie Interstellar was a really good, really good rendition of what a black hole looks like. And that's what happens when you get Nobel laureate Kip Thorne to be your scientific consultant on set. You'll get everything right. Now, how do we know black holes exist? For a long time, astronomers just thought this was a mathematical curiosity of general relativity, and that black holes don't actually exist. But in recent years, we've gotten some very good pieces of evidence for black holes. Of course, the big piece, we got the first ever picture of a black hole just a few years ago, I think in 2019. And that was of M87 star. This is a 6 billion solar mass, 6.5 billion solar mass black hole in the elliptical galaxy Messier 87. This was taken by the Event Horizon Telescope. This is shown in radio, where at the center is that black dot at the center. That's the black hole. And then here's the accretion disk around it. Now, for scale, XKCD, the famous webcomic, put the solar system on top of it. So Voyager 1 has made it to the, has quote unquote made it to the event horizon of the Messier 87 black hole. There's also a black hole at the center of our galaxy. We'll talk about this a little bit more next week. We call it Sagittarius A star because it's in the constellation of Sagittarius. And it is not as massive as Messier 87's. It's only about 4 million, not billion, but 4 million solar masses. And we haven't taken a picture of it yet. We are working hard on that. But what we have done is we have looked at the orbits of stars at the center of the galaxy. And we see stars that are moving at incredible speeds. And we actually pinpoint the size and the placement and the mass of the black hole at the center of the galaxy by watching the stars. Here's a little movie showing the stars moving around the black hole. I mean, these are stars going very, very fast. Stars don't move this fast unless they're near a huge gravitationally attractive object. There are other extreme events. The only other extreme event in the universe that we'll talk about tonight are gamma ray bursts. Seriously, back in the 1960s, as the United States launched top secret satellites to look for gamma rays emitted by nuclear bomb tests by Russia and other countries, those satellites detected occasional bursts of gamma rays lasting for just a few seconds. And it took several years for military scientists to be convinced that these gamma ray bursts were not some sinister human organization, some country doing huge, massive tests, but instead they were coming from space. And they made that discovery public. So the military discovered these first, and then science was brought in. These are gamma rays bursts of unimaginable power coming from space. If a gamma ray burst shine equally brightly in all directions, then its total luminosity would briefly exceed, just for those few seconds, the combined luminosity of 1,000,000 galaxies. These are absolutely insane events. I've been saying that a lot tonight, but it's actually true. These are insane events. Thankfully, they're not shining in all directions. They're just doing one burst in one direction, we think. And we think these gamma ray bursts, these long gamma ray bursts, are caused by stars just directly collapsing into black holes via not a supernova, but a hypernova. Meanwhile, short gamma ray bursts lasting less than 2 seconds are thought to come from neutron star mergers. Here's an image of that Hubble was able to take of a gamma ray burst back in 2013. There's a nice galaxy. You can see the gamma ray burst they're pointing to. The gamma ray burst exists in the top right image, right where the arrow is pointing. And you can see the difference. There's a bright spot where the arrow is pointing in June 13th, 2013, and no longer on July 3rd, 2013. That was where a gamma ray burst, maybe a new black hole, just formed over there. So these are incredibly massive, powerful events. So since this is the end of our stellar little mini series, before we move on to galaxies in the universe, let's just review all the things that we've learned so far. So stars form from molecular clouds. As molecular clouds condense and fragment, they're able to form stars, usually in clusters, in beautiful nebulae as well. Those protostars, once they reach that magical temperature of 10 million Kelvin in their cores, they can start fusing hydrogen, and we get a star. Now, the defining characteristic of a star is its initial mass. That determines what it's going to be doing for the rest of its life. So if it's way too low, if it's a low mass star of less than 8/100ths of our sun's mass, then it will be a brown dwarf. Very similar to just a really, really massive planet. And it just will hang out there forever, won't do anything. If it's a low mass star, around our sun's mass, what this diagram is calling anything less than 8 solar masses, then it will live for on the order of 1 billion to 10 billion, maybe even several hundred billion years. And as it evolves off the main sequence, it will become a red giant in its old age. And then either it will cast off its outer layers into a planetary nebulae with a white dwarf at the center. Or if it's in a binary system with another white dwarf, then its outer layers will be stripped by that white dwarf, either resulting in a white dwarf supernova where everything gets blown apart and nothing is left, or maybe just a series of novas as hydrogen fusion happens on the surface of that white dwarf. Regardless, that white dwarf will then go on, just radiate away its energy and eventually form a black dwarf trillions of years in the future. If it's a massive star, those will live for a very short time, maybe 10, 100 million years. That's million with an M. They'll quickly form red supergiants, and then fusing heavier and heavier elements, hydrogen into helium, helium into carbon, carbon into oxygen, neon, silicon, sulfur, all the way up to iron. Once it produces iron, then it will die and explode as a supernova. Well, we'll get left behind a beautiful supernova remnant, perhaps with either a neutron star or a black hole at the center. Maybe that neutron star will be a pulsar. Maybe that will be in a binary system. Maybe we'll get a black hole. That will depend on the mass of the remnant. So that is kind of a quick and dirty summary of everything we've talked about these past few weeks. As always, we're talking about astronomy, so you can go out and actually see these things. And then you'll probably need a telescope for the objects I'm about to recommend you go see. You can go see planetary nebulae with a small telescope that you buy at like Walmart. You can do that. And tonight and in the coming days, there will be 2 planetary nebulae that are very easy to spot with your telescope. The first one is the background image for this talk, the Helix Nebula, in the constellation of Aquarius. So tonight, if you go up around midnight in the southeastern skies, you should be able to find the Helix Nebula, actually right below Jupiter, conveniently. And if you can't, you've seen what it looks like. It's been in the background of this talk. Another one you can look for is the Dumbbell Nebula, also known as the Apple Core Nebula, also known as Messier 27. This will be visible earlier in the night, so maybe around 10 or 11 o'clock. Summer sucks for observational astronomy because it doesn't get dark till like 9. But if you look at the eastern, southeastern skies and the constellation of Vulpecula, just above my favorite constellation, Delphinus the Dolphin, you will be able to find the Dumbbell Nebula. If you can't find it, here's what it looks like. It does sort of look like an apple core where the bites have been taken out of the sides here. It's a great target for amateur astrophotographers. So I definitely encourage you to go outside tonight. See if you have a telescope, try and find these planetary nebulae. If you don't have a telescope, go outside and just try to identify some constellations. If you know maybe 20 or so constellations, it will become as familiar to you as your own neighborhood. I definitely encourage you to go do that. So with that, we're done with our little mini series on stars. Next week, we will start talking about our own galaxy and then the rest of the universe. So we're ending our little series. But as always, please comment down below, like, comment, subscribe. Let me know if you have any questions. If you have any concerns, if you didn't understand anything, I'd be happy to answer them. And as always, I will see you all next week.